Hello and welcome. So today we're going to talk about inductive types. More precisely, inductive types as they are implemented and used inside of the Lean 4 proof assistant. If you don't know, Lean is a computer language and a system that lets you formally verify mathematical statements expressed in the language of type theory. And recently, I've been getting some experience with this powerful tool because it's very cool. But I also think that it will have a huge impact on the mathematics of the futures and how they are done. And, I want to be part of it. So, okay, I wanted to talk about inductive types, which is an idea in type theory, a very important idea. So I wanted to talk about it with the help of this tool, Lean, because I believe it will make stuff clearer. Like in all meanings of the word, I believe it will make stuff clearer. However, I do recommend checking out the Lean documentation. So my goal here is not to make a tutorial on how to use Lean and how it really works in its intricacy. It's a powerful tool, it's a complicated tool, but I do recommend checking out the Lean documentation because it is so well written. I'll put a link to some canonical resources in the description, but you should definitely look at them if you are interested. So, like I said, my goal today is not to do a Lean tutorial, nor is it to explain in great details what inductive types are. Basically, it's just to nerd out with you over a bit of type theory that I find interesting and somewhat mysterious. So, this means that this video will probably be more interesting to you if you already know a bit like how Lean works, and also if you are already familiar with classical set-based mathematics. So I do believe that maths is done rather than read about, and I hope this video may be an example of that. And basically that you can learn from how I do maths in this proof assistant, that it can be of some value to you. So without waiting any longer, let's begin. The plan here is it's quite simple. We're just going to build a little bit of the mathematical edifice that one is used to in classical maths. So my idea here is we'll start with defining or encoding Cartesian products into type theory. So usually, we're speaking of Cartesian products of sets, but here there are no sets, we only have types. So just welcome in VS Code. This is where we will be writing our code that Lean will type check, and we will see a lot of interesting information here in this info view. So this is the environment in which we will be working today. Welcome. So let's get back on the task, which is we want to build a representation for pair types, basically. So I was saying Cartesian products, pair types. So the first thing we're talking about is inductive types. So the way to define such a type in Lean is with the keyword inductive. Okay, so inductive, we'll call the type pair. And we need to specify, like, it's going to be a pair of which type together with which other type. Right? It's not like in set theory you could you wouldn't have to worry about types. But here we do have to worry about types because it's called type theory. So it's going to be a pair of things that have type alpha. Alpha is a type. And things that have type beta. And just as an aside, but you probably already know this, but notice that everything in Lean has a type, including types themselves. Here we see an instance of that. We want alpha to be a type, so we say alpha has type, okay, easy enough. In fact, we're just going to define some universe levels, U, V, and W. Yeah, sorry guys, I just want to say I'm getting used to a new keyboard, so I'll be writing quite weirdly sometimes. Like, it's possible I will type some Japanese characters. Don't worry about it. Okay, so alpha is a type, and we can put a universe parameter here, U, and here V. And then we can specify what are called constructors. So we write where, and then constructors. A pair type has, well, the way we want to build stuff, the canonical way to build a pair of things is by calling a function that is a constructor for this type that we will call mk for make. And make will be a function that takes two arguments, okay, one argument of type alpha and another argument, one argument of type beta, and will produce something that has type pair alpha beta. Okay, so this constructor right there, mk, as it stands, it's the only way to construct something that has the type pair alpha beta. It's the only way. But if I give you something like anything, let's say P that has type alpha beta, and that's the only thing you know, would it be possible somehow that P is not of the form mk something something? I mean, a priori it's possible, right? That there would exist some far out term somewhere in the type pair alpha beta that would exist and that would not be written as mk of something something. But as we will see in a moment, we can prove that every term of the type pair alpha beta is of the form mk of something something. So that's kind of interesting, but before we get to that, we need to talk about the recursor. So the recursor is the cornerstone of inductive types. We can check here that Lean has generated for us mechanically, right? It's all automatic. It's part of the theory. It has generated for us something that's called rec, and this is the recursor. And the recursor gives us the only way, really the only way to use the type we've just defined. Okay, so the most important aspect of any type is not what it really is. The most important aspect of any type is how do you use it. And this little function here that is generated for us, it tells you how to use a type. What does it mean to use a type? It means how do we build a function, how we construct a function from the type we've just defined into any other type. And if we look at the signature here of this rec function, we can see it's okay. So there's a lot of pieces, moving pieces in this signature, but it's not complicated. It's complex. There's a lot of stuff going on, but it's not complicated. The first two parameters here are just the types that go here. Let's pause this. So these two here, they are just like, okay, we're going to define a function from pair alpha beta, but what are alpha and beta, you know? So this is where you tell the function what alpha and beta are. So this is not super interesting. Let's just how can I do this? Let's just create some variables alpha beta, and then in alpha, oops, like that. Okay, and we're going to write this type like a bit in a simpler manner. The first real parameter that you can give to this function here is the motif. The motif is quite interesting, but it has got something to do with type families. So the idea here is we want to construct a function from a pair type into any other type, but the target type could, in theory, it could depend on the actual value that we feed into the function, right? Like if we feed some specific pair, then we could produce like a natural number, and if we feed to the function a different pair, then we should be able to produce like a string or something, right? So we allow the target type to depend on the value that we feed into the function, and this is the idea for this here, the motif. So as you can see, it will take something of a value of type this, of a pair type, and will produce a type. So it's a function that produces types. Why not? And you can see here, this, let's give us a bit more space. Okay, so this is the motif. It's important, but it's a technical aspect. This is why it seems kind of weird, but yeah. The real, let's say, the realest parameter that you can feed the function rec is this here, and it says given a value a and a value b, right? Here it's written a_1, but just imagine it's written b because it's a type beta. So we have two terms, one of type alpha and one of type beta, and we don't know anything about them, only their types, so they are completely arbitrary. We can construct something of type motif pair dot mk . So basically this is pattern matching in some sense. It allows you to define, like to construct something of the appropriate type, okay, using, like pretending that the term is written as mk of something something, and the first something is here and the second something is here. And this is saying that if you can build such a function, then it suffices to do that to get a function here that will work for everything that has type pair AB. Okay, so to build, like, let's say that in some different way, to construct a function from pair alpha beta into anything you want, it suffices to specify what this function should be on things that have the form mk something something. Okay, and this is really important. Like, this is the essence of the inductive type in some way. Okay, so I'm kind of guessing that my explanation wasn't that clear, so maybe if we actually use this function, this recursor, then maybe things will be clearer. So okay, let's make this live. And you know, when we have a pair, it's usually interesting to like break it up into parts, and this is the purpose of the projection functions usually, right? So we can define like, okay, we will define some functions here, but it's better to put ourselves in some namespace so that every function that we define in the namespace will be prefixed with pair. So the way to do that is just namespace pair, right? And we end this namespace as well. Okay. And now we define something that we call the projection, let's say on the first coordinate. So what is going on here? What is the signature of this thing? It will be a function that takes anything that is a pair and that produces something of type alpha. Okay. Let's not define it for now. We also have the second projection, right? That will take anything that is a pair and that will produce something of type beta. And we sorry that as well. Okay, so let's define this here. We will use the expanded form of the recursor. Well, I don't know how to pronounce that, but the recursor, I guess, which makes every implicit parameter, which is delimited by these curly brackets. So when we use the @ sign, we have to explicitly specify the parameters, and this is just because I want to like explicitly write what is the motif here, but usually we won't write it ourselves because Lean is smart enough to figure out what it should be. So the motif is a function, right? So let's write it as a lambda abstraction, a function that takes some pair that inhabits the type pair alpha beta, and then it will map it to something. If we put a hole here, we can see it should be something of this type, which is incomprehensible, but we know what it should be. It should be just alpha. Okay, is that right? What's going on here? Oh yeah, it's not happy. I'm not sure why. Like oh yeah, sure. That's because the actual first argument is alpha and the actual second argument is beta, and then comes the motif. Like it's written right here in the signature, right? I forgot to pass this and this, but now I did. Then I give this, which is this, and it will basically just ignore what is the pair value that we give it and just produce it will produce every time the same thing, the type alpha. Okay, and now what we need to give it is this function here. So this function, I will also write it as lambda abstraction. It will take some x and some y and produce something, and we can see here in the info view what this something should have as a type, and we see it should have as a type just alpha, right? Because this is a function application on we don't really care what it applies it to because it just returns alpha every time. So this is alpha. So we need to produce a value of alpha, and if we look at our context here, the only thing we have that could possibly be used to produce such a value is x. So we are forced to just say this is x, and then we're done. Yeah, so this is enough to define a function on all pairs. Just specify like what it does on when you know what are the values in the first component, which is x, and the value in the second component, which is y. there's a problem here. Oh yes, so the thing is, Lean is a programming language, right? It will try to compile stuff into executable code, but we don't really care about that right now, so we can just say it's non-computable, and it should be happy. Almost there's some warnings here because I didn't use these variables, but here we don't really care about this, so I will just put we can set this option here so that it doesn't scream at us because we didn't use variables. Okay, for this here we can do the same thing basically, just copy paste and it would work. There are other ways to define such a function. We could do it like using a match statement. Match statements do compile into the recursor, but I want to use the recursor again, but we will use the implicit version of it without having to specify ourselves what the motif is. So the only thing we have to give to this function is what happens to the pairs when we know how they, like what information is contained in the pair. And to this we will say, okay, we know the pair is made up of x and y, and it should produce something. Let's put a hole there. It should produce something of type beta, as you can see. And in our local context, the only thing that we can use to produce such a value is y. And this is obviously what we want to do, because this is the second projection that will extract from a pair what is the second component. But the same problem arises here, so we'll just write non-computable so that Lean doesn't try to compile it into executable code, and we are good to go. Everything compiles. Well, okay, everything type checks, so everything is perfectly fine. We have two functions that we can use to break up a pair into two things. Now remember I said, would it be possible that some term of pair is not of the form mk of something something? Like, couldn't it be possible that some term is inaccessible somewhere in the pair type? I mean, it could be, but we can actually show. So let's make a theorem. We can actually show that every pair can be written as mk of something something. So let's call this unique, and this statement is going to say that for every pair, let's write it like that. So for every pair we have that p is equal to let's just say mk p dot proj1 p dot proj2. Okay, and now to prove this, there are many ways. We could use the recursor, so let's do that. We will use the explicit version of it so that you can see what the motif is. So the motif should take some pair. We don't know the structure of it, but some pair, and just produce a type. Okay, and which type should it be? Well, let's look here. We want to prove this. We want to construct a term of this type. So this can be interpreted as a function, right? This is a for all, so it can be interpreted as a function. So the type we want to build is this. Oops. Okay, this is what we want. Now, of course, we should probably introduce the pair. So p map. Let's let's write it like that. And now we need to tell Lean how to construct the correct term when we know how the pair is written. So we know we have something of the form pair, or we have something of the form mkxy. So let's see, let's put a hole here, and we need to produce something that has this type. Right? But if we can simplify this. This is like if we add a type annotation here, we can see this is just we need to show this. Sorry. Right, we need to show this. Is that right? No, it's not. Wait a minute. Right, okay, sorry. So we need to show, I'll just let me put pause here. I just want to read this. So I need to apply this function. This function right here is going to be applied to this. Right, so every instance of P in here will be replaced by an instance of this. If we write what this should be a hole with type mk xy is equal to mk xy. So what am I writing? This is not working out. Okay, let's think about this. So if we try to figure out what this should be, well, let's imagine every instance of P here is already something is this. Let's imagine we need to build a type. Build a term of this type where every P is actually this right here. So how could we do this? Well, here what's going on? So if we have parentheses mkxy parentheses dot proj1, well, what is the definition of proj1 here? It's defined using the recursor, right? And the way a Lean is set up is when you apply like the recursor to something of the form mkxy, this is computationally equal or definitionally equal to simply x, right? Like there is no difference for Lean between this and just x. So this the same is true here, right? There is no difference between this term and just y. So for Lean, this whole thing here is just going to be the statement mkxy equals mkxy, and this is easy to prove, right? It's something is equal to itself, so we can prove that using the reflexivity of equality. This is written like that. So this works. Okay, and there's a problem here because this produces a function and we want to apply this to P so that everything type checks. We can also eta reduce because this is a function that takes P and then apply P to some other function. So this is exactly the same thing as this function right here. And yeah, and this is the proof. All right. So we have shown that for any term of type pair AB, we have, like, it can be written in this special canonical form here, right? So this gives weight to the idea that in an inductive type, the constructors they freely generate the type. So this is the big idea, right? This is kind of why it's called inductive type, because it's as if you would start with nothing, like an empty box, which is called pair, and then you build up elements in this type using only the constructors. The constructors are, in a sense, the only thing that you have to build these objects. So yeah, the way I really see it is like I said, that an inductive type is freely generated by its constructors. And you know, if we had multiple constructors, then we could build up terms using one constructor applied to another one, and then it would be like we could do more complicated constructions. Here it's really simple, you know, we can only apply the constructor to something here and something here, and then we get the appropriate thing. And everything that I've just said is really encapsulated in this theorem here, which I think is pretty neat. You know, it's pretty cool. So this is we could prove stuff about the pair type. Like, if you think about it, the recursor here, if you look at its form, it says that functions from the pair type into anything you want correspond in a natural way to functions like that, right? So let's write it in a better way, maybe. So how can I do this? So the pair dot rec alpha and beta. Yeah, so it's going to yell at me because I need to have to really tell it that there are some, these are types, and they are in the context now, and the type of this, well, it will take the motif, which are alpha, beta, right? And we'll, let me write it in a better way, you know. Let's put this here, and this is going to be indented like that. And then next parameter that we need, like I said, is going to be some function that takes something of the alpha and something else of beta, and will produce something motif of mk xy, right? And all of this, if you give it these two things, it's going to give you, in return for your efforts, a function defined for arbitrary elements of the pair type into your motif. And of course I need to give a name to this value here. There we go. Okay, so this is a better way to write, this is a better way, in my opinion, to write the type of the recursor. Maybe I should have done that earlier in this video, but oh well. Now you can see that to construct this function from that will take any value that has type pair, it suffices to construct an element using the knowledge of a value in alpha and a value in beta. So this is basically the universal property of the like the product, not the usual one, but it's basically the definition of the exponential object in category theory. So you have this natural isomorphism between like maps out of the pair type and maps from alpha into this type here of functions from beta to something else. This is basically, this is just the definition of the exponential object. Usually people, when they talk about the universal property of the product, they have in mind the one that allows you to talk about maps into the product. Here we're rather talking about maps out of the product, so it's like expressing the product in a different way. But my point here is that the recursor can be seen as a way of stating a universal property for the type that we are defining. So in the case of the product, we see that we define functions out of pair types as being equivalent to functions that can build something using like the components of the pair. You see, this is exactly what this is saying. Yeah, so this is a small introduction, or maybe just talking about inductive types. I wanted to talk about more, but I'm starting to get very tired, so I'll keep what I wanted to talk about for the next video or something. Like my project from here is to talk about dependent pairs next, and using dependent pairs we can really start doing mathematics. Like we can easily start doing algebra, because we can define structures on types. For instance, we will define the structure of a unital magma on a type and use that to formalize the Ekman-Hilton argument that is used a lot in mathematics. But we'll keep that for next time, and I hope this was interesting, and see you next time.